All right, here we are again after a long spring break. And of course, now we're not even here in person. So yeah, yesterday my eye was so puffy and swollen I could hardly see. So I thought it'd be a smart move to stay here today. But now, of course, I was going to give you your exams back, but I guess you know that I was able to put the grades in Blackboard. There's a grade book in there somewhere. I don't know exactly how you're supposed to look at it. I only see my side where I put them in. But I'm pretty sure you should be able to see your grades even if you haven't looked yet. You could go double check. So that way, at least you know how you did. And then I'll hand them back on Friday, of course, so you can see the actual questions. And then at that time, if you want to, we can go over some of the questions if you're not sure why you got points off and that type of thing. But for right now, we'll just carry on with the new material. And so it's been a while, but when we left off, we were looking at chapter 13, which, by the way, 13 is the entire content of the second midterm. So it won't be much longer before we have the second midterm, maybe 2 or 3 more weeks. My goal is to make sure we get it in before Easter. And I don't think that'll be a problem at all, because even though it's a fairly long chapter, it is just the one chapter. So, and we've already done 13A, where we discuss testing hypotheses about the population variance. You might recall it was a very straightforward procedure. And we also introduced the chi-square distribution. In this section, we're looking at hypothesis tests that are known as goodness of fit, because what we're trying to do is demonstrate whether or not a particular set of data follows a probability distribution, such as the normal or the Poisson or the binomial. And so it's a little bit different than what we're used to seeing. What we have to actually do, and we did actually start to go over an example just before the break, is take the data that you're given and calculate what numbers you would expect to see if the data really followed the distribution that you're interested in. And then you compare the two. Now, as it turns out, let me get my calculator out. Your calculators actually can help us with this, even though it looks like it's going to be a lot of work, and it would be, except that the calculators have a nice feature built into them that lets us do this a little more easily. So when we get to that point, we'll take out the calculators and start using them. But for now, let's go back and review quickly that in cases, goodness of fit tests, you write the hypothesis as, let's say, for example, you're testing whether or not your data are normal. The null would be that the population is normal, and the alternative would be that it's not. And that's the way it's set up. It's just yes or no. And so because of the way it's set up, these are always right-tail tests. So we don't have to really think about that part of it. The new part, though, is that you'll be given a set of data, and you'll be asked to calculate the expected values that you would get if your data followed a particular distribution. So we started to do this one in class. We had an example where we're trying to find out if our telephone call data follows the Poisson distribution. Now, as you know, the Poisson distribution is based on the parameter lambda, and lambda is the average number of events that occur per unit of time. So let me just skip ahead and see if here it is. This is the formula that you use to calculate Poisson probabilities. And of course, that lambda there, that Greek letter lambda here, is the average number of events per unit of time. So for this particular example that we used, we were told that we took a sample of 75 hours, and in those 75 hours, we observed how many phone calls there were. And as it turns out, in every case, there was anywhere from 0 to 3 phone calls. There were no hours with 4 phone calls. So this is all of our data. And the results are here. We had 29 hours with no phone calls, 23 hours with 1, 17 with 2, and 6 with 3. The question is, does this data follow the Poisson distribution? All right, well, it's a good question. It might be Poisson and it might not be. It's hard to say just by looking at it. I mean, unless you do this stuff all the time, it's hard to see what the numbers are supposed to look like unless you sit down and calculate the actual probabilities. Now, with this example, we have a wrinkle that we have to deal with. In order to calculate Poisson probabilities, we need to know the value of lambda. And sometimes when you're testing hypotheses about the Poisson distribution, it'll actually specify in the null hypothesis what lambda is. Here it doesn't do that. It just says, is it Poisson? Is it not? And that means, is it Poisson with any lambda? Okay. So in other words, we don't really care what the lambda is. We just want to know if the data is Poisson or not. So that means we have to calculate the lambda ourselves. All right. Now, if instead, let's say it had said the null is that the population is Poisson distributed with lambda equals 2, then we don't have to calculate it ourselves. We just use that as our lambda in all of our calculations. So it could go either way. We might be asked to calculate the lambda ourselves, and we might not. It depends on whether it's given to you in the problem. So here it was not. So that means we have to take it on ourselves to calculate the mean number of phone calls per hour. That would be our lambda. And since we have different numbers of frequencies, we can't just add up 0, 1, 2, and 3 and divide by 4. We have to construct what's called a weighted average, which means we're taking into account the fact that we have a lot more zeros than threes. So how do we go about that? Well, what we actually did was in the, actually, let me quickly pencil this in here. The formula that we're actually following here is this. All right, X bar. In the numerator, you have the sum of weights times the X's. In this case, that would be the numbers of phone calls. And in the denominator, you add up the weights. And this is known as a weighted average. So in other words, each X has its own weight associated with it. So if we go back to this table, these would be our X's. They could think of this as X1, X2, X3, and X4, and then these would be the corresponding weights. And so the goal here is that you're going to, in the numerator of our formula, we'll multiply these together and add them up, and the denominator will simply add up the weights. And when you do that, you can see, and we did this in the class, you're going to wind up with 75 in the numerator, 75 in the denominator. So that tells us that lambda equals 1 in this problem. Well, that's good because we need that to come up with our answers. Now that that's done, what we're going to do next is calculate some Poisson probabilities for each of these 4 cases. All right, so again, we're trying to find out the probabilities of X equaling 0, 1, 2, and 3 when lambda equals 1. And so using this formula, we can come up with these values. Or what you could do is use the calculator. And we went through that in the class. Let's go through it one more time since it's been a while. What you're going to do is go to second vars, as is so often the case. And the function you want is way down ways. You have to scroll all the way down to number C, which is Poisson PDF. Now, by the way, make sure you pick PDF. There's a CDF in there too. Do not pick it. And when you get there, it's going to ask you for the lambda, which is right here. And in this case, we're looking at 1. And then it'll ask you for the X value, which depends on which one you're looking at. So let's say you're looking at 0. So you plug that in, and that comes up to 36.3679, let's say. So this shows that Px equals 0 is 0.3679. Okay, and then of course you follow them all, do them all the same way. Hold on one second. I want to make this as neat as possible. All right, and then you would do them all the same way, and you would come up with these same numbers after rounding to, let's say, 4 places is probably good enough. Now, that's not enough though, okay, because this is the probability of falling into this category, but we have a sample size of 75, which we have to incorporate as well. So what you're actually doing here is you're multiplying the probabilities of being in that category times the sample size. So you can see I've done that down here. And what that means is that if the data is really and truly Poisson with a lambda of 1, then you'd expect that 27.59 times out of 75, we get no phone calls. And then same thing for 1. For 2, we'd expect this to happen 13.79 times. And for 3, it's 4.6. Now, you're probably wondering, by the way, why we don't round these up to the next nearest integer. In principle, you should, because these are phone calls, but the loss of accuracy would be so great that it would make the test a lot more, the results would be a lot more questionable, let's say. So in practice, what we'll do is we'll keep 2 decimals or 2 digits after the decimal point. And now once that's done, we're going to compare this to the actual phone calls we got. And notice that these are called expected frequencies. The actual numbers are called observed frequencies. Okay, so we're going to build a chart where we have them all together in one convenient location, like here, right here. And so this way we have them all side by side. And, you know, just glancing at them, you can see they do look pretty close, don't they? But that, of course, is not good enough. We need to be much more precise than that in statistics. So we're going to construct a test statistic from these numbers. And how are we going to do that? All right, well, first of all, let's go back and revisit the test statistics so you can see why we're doing this. The test statistic requires us to do this, which means go through the entire list. And we're basically comparing the O's and the E's. The O's are the observed values, and the E's are the expected values. The subscript J refers to which category we're in. So let me fill these in. So you can see, for example, this is O1, O2, O3, and O4. This is E1, this is E2, this is E3, and this is E4. And now you just plug them into that formula. Now, we can certainly do this. It's not difficult, but it is time consuming. So that's why, see, this is what you would do. And you can see we end up with 2.0085. Now, we know from experience that 2 is a very small number on the chi-square distribution. It appears that we will not be able to reject this null hypothesis, but we do have to formally compare it with our test critical value rather. Now, before we do that though, well, actually, I'll tell you what, let's do that, and then I'll come back to the calculator. The critical value is a little interesting. Here's what it looks like. Now, the chi-square distribution, because we have the square here, we need both the alpha and, which of course is our level of significance. And then down here we have our degrees of freedom. Because remember with the chi-square distribution, the entire distribution is characterized by the degrees of freedom. Now, what do these letters represent? K is the number of categories. In this case, each possible value of the phone calls is defined as a category. So in other words, we actually have 4 categories here. 0 phone calls, 1, 2, and 3. So there's altogether 4 categories. If you prefer, you can think of them as simply columns. How many columns are there in our data? So in this example, K is 4. Now, the 1 is obviously 1. Now, M is the interesting one. M refers to how many parameters or values we had to estimate from the data ourselves. So in this example, since we had to calculate lambda from the data, m equals 1. Okay, now there's one value that we calculated. If it had been given to us in the null hypothesis, note that down here. Then m would be 0. All right, so think of m as how many values were we required to calculate ourselves from the data. So in this case, k is 4, m is 1. So the number of degrees of freedom, k minus 1 minus m, is 4 minus 1 minus 1, which is 2. So now, so with 4 degrees of freedom, 2 degrees of freedom, we looked this up in our chart, which we also looked at last time. And remember with the chi-square tables, the area is always in the right tail that we're looking at, unlike the others that we've seen before. So in other words, we're looking for the right 5% of this distribution. When alpha equals 5 with this chi-square distribution, that means 5% in the right tail. So the combination of 5% in the right tail and 4 degrees of freedom gives us a critical value of 9.488. So if the test statistic is greater than that, we reject the null. Okay, now that didn't happen here, did it? It did not. Okay, in fact, it wasn't really even that close. 9.488 is way out here. Oh wait, what happened here? I got something different. Uh-oh, hold on a second. You have 5%. Did I? Oh, you know what I did? I don't know why. I went to 4. Sorry, I don't know what that was all about. I completely goofed it up, didn't I? It's not 4, it's 2. No wonder. It was 2. We went through all those calculations and I still messed it up somehow. All right, no, it is 5.991. The degrees of freedom is not, I was looking at K, that's why. The K is 4, but the degrees of freedom is 2. Okay, so I've got to change that now. 5.991. This, of course, is our rejection region. But the test statistic is 2.0085. So now remember the way this test is set up. It's a very different approach. The null is that the population is Poisson. The alternative is that it is not. So normally the null is set up so that if you reject the null, you're essentially proving something that you were hoping to find. Here it's really the other way around. It's basically set up so that we'll assume that it is Poisson unless we have proof that it's not. And that's a consequence of the way the test statistic is calculated. Okay. So anyway, so in this case, because we cannot reject the null, that means our conclusion is that the data really do follow the Poisson distribution with lambda equals 1, okay? Well, actually, the null was simply that it's Poisson, so we'll leave it at that. But we know that it is lambda equals 1. Okay, so let's just say the data are Poisson. Okay, so that means we have enough, we don't have any evidence to suggest otherwise. In other words, it's like we're saying that it looks like they're Poisson, but we do not have enough evidence to suggest that they're not. Okay. Now, I alluded to earlier the possibility that we could replace some of this, at least, with the calculator. So how would that work? All right, so here's what you're going to do. We're going to do the following. Set up two lists. L1 will be the observed values. L2 will be the expected values. All right, so let's go get the table back so we can do this. So go ahead, go get your lists. Actually stat tests edit, sorry, stat edit. Go back and erase all the lists you already have now. And what we're going to do is in L1, just type those four numbers, 29, 23, 17, and 6. And then in L2, put 27.59. Again, 27.59. 1379 and 4.6. Okay, and when you get out of that mode, we're going to do something very interesting. Something you might not have even realized was down there. All right, so let me write these instructions in here. Hopefully you're all caught up, typing. All right, so let me scroll down and start entering the instructions here. So here's what you're going to do. We're going to go to stat tests. And if you scroll down the list, oh, look at that D. And then it'll say chi-square. Let's see if I can find chi here. I'll use that one. That's close enough. Chi-square GOF. Now, what do you suppose GOF stands for? Goodness of fit. Okay, chi-square goodness of fit tests. Test. Okay, so you pick that. And when you get there, what you're going to notice is that it's asking you for observed and expected. Now, it may already say these. I think by default, it says L1 and L2. Then you have to tell it the degrees of freedom is 2, like we did. So go ahead, just change the DF to 2. And, oh, what happened? Oh, it's right there. Okay, so first things first, you'll notice that it's going to give you chi-square is about 2.0. That's the test statistic we did earlier. But here's the other thing. It's giving us a p-value. About 3.662, which means that we, of course, do not reject. But if you also notice directly below it, it says CNTRB. What it's doing there is that it's going back and it's showing you each one of these individual terms if you're interested in knowing how much each of these terms equals. It's listed separately right there. Okay, if there's some reason why you need to know that, that's what that's for. But as far as we're concerned, it confirms that we did the test statistic correctly. And it also gives us a p-value so that we can use that information to conclude that we cannot reject the null, and therefore the data follow the Poisson distribution. Okay. So since the p-value is greater than alpha, we do not reject the null hypothesis. The data follow the Poisson distribution. And that's it, you're done. Oh, that was nice. That wasn't hard at all, was it? No, it was a little time consuming, and we had to obviously learn the steps, but it's not all that difficult. It's just that you have to calculate the Poisson probabilities. I don't think there's any way to avoid that. I don't believe it's capable of doing anything more than that, but it's still saving us some time by calculating the test statistic for us and then turning that into a p-value. I'm not absolutely convinced that the calculator can do p-values with the chi-square by itself, so this is often useful. Now we're going to look at another case, and this time we really are using the normal distribution. Okay, the basic procedure never changes. What will change is the way we calculate the expected values. Like, here's a simple one. A portfolio manager wishes to determine if the returns to his portfolio are normal with a mean of 5% and a standard deviation of 10%. So let me just jump ahead here and show you how this would be expressed. The population is, the null is that the population is normal with a mean of 5% and a standard deviation of 10%. The alternative is that it is not. Yes or no. And again, it's a right tail test. And so we'll assume level of significance is 5%. Now, here's the data that we have. And I've broken it up into ranges. So altogether, if you look at the frequencies, you'll see that we have altogether 100 observations. Okay. Of which, all of which fall into one of four categories. The loss between 15 and 5%, somewhere between a loss of 5% and a gain of 5%, a gain between 5 and 15%, and a gain between 15 and 25. Now, since the normal distribution is continuous, we cannot have individual values. We have to have ranges. That's why it's set up this way. And I've kept it simple. There's only four categories. In principle, you can have any number of categories that you like. So as you can probably guess, what we have to do now is calculate normal probabilities for these four ranges of returns, given a mean of 5% and a standard deviation of 10. Now, you might remember that, yes, you can do this with your tables, but you might also recall that we can do this with our calculators. And this we've done many, many times. All right, so let me skip ahead here a little bit. I'm going to sneak in a new slide here. In order to use TI 84 rather, to compute the normal probabilities, choose second vars, and the one you want is normal PDF. Normal CDF, number 2. By the way, I just want to point out that with continuous distributions, we always use CDF. With the discrete distributions, we always use PDF. Okay, so you know from experience that when you hit normal CDF, it's going to ask you for 4 things: lower, upper, and mu and sigma. And then you have your you of course hit calculate, and you'll end up with the correct answers. Now, once you have those probabilities, you're going to go ahead and calculate or multiply the probabilities by the frequencies to come up with the correct value. So, for example, what's the probability of having a return between minus 15 and minus 5%, given that the mean is 5 and the standard deviation is 10? All right, so let's sneak that in here. By the way, I think we should always use decimals. And so we'll go through. And the lower is negative 0.15. The upper is negative 0.05. The mean is 0.05. That's right, isn't it? I forgot already. And 10, right, 5 and 10, perfect. And you should get, let's see, let's go through that. Lower is negative 0.15. Upper is negative 0.05. Now the mean, the default here is 0.05 for the mean. Change that to 0.05. I mean, the mean is 0 by default and the sigma is 1. So you have to change those two. And let's see, that turns out to be about 0.1359. All right. So what I'm going to do is quickly take advantage of PowerPoint's wonderful capabilities here. There's no need to type it over again 3 times. Now, the next category is from negative 5 to plus 15. Sorry, to plus 5. So I only have to change these two. All right. So you change that to negative 0.05 and positive 0.05. And then, whoops, run it again. 0.3413. And then for positive 5 to positive 15. And so now this time it turns into it's again 3413. And then everything from positive 15 to 25. Oops, no, that's not what I wanted to do. This is it, yeah. So let's try that one. Point 1359 again. Okay, so those are done. And then what you have to do once you have those probabilities is you copy them into this table. And in order to calculate the expected frequencies, you see there's the 4 probabilities. And you're going to multiply them all by 100 to come up with the expected frequency. 1359, 3413, 34.13, and 1359. All right. Then, of course, you're going to bring them together onto that same table we had before, where we're directly comparing the observed and the expected frequencies. Okay, so I'm going to scroll ahead and show you that. Now, once we're here, you've got one of 2 choices. You can go ahead and do the test statistic in the traditional way by plugging them in, or you can plug these into list 1 and list 2 and come up with the correct p-value. All right, so I'll tell you what, why don't we do that right now, just to get some practice. Go back to your lists. And let's see. Replace what's in there with these. And so this first one is 22, 29, 37, and 12. Over here in list 2, you have 30, 13, 15. I remember always 2 places. 34, 13, 34, 13, and 13, 59. And then now, of course, we go back to stat tests, chi-square goodness of fit. All right. Oh, one more thing. I almost forgot. We still need the degrees of freedom. So let's come down here. The degrees of freedom is k minus 1 minus m. Now, this time we had 4 categories again, but we did not have to calculate any of the values, which in this case are mu and sigma. It's possible in these cases you might have to do that yourself, but we did not here, so m is 0. And because m is 0, that means when you calculate the degrees of freedom, you're going to have 3. K minus 1 minus m is 4 minus 1 minus 0, which is 3. And if you go to the table, in that same column, directly below the 5991 with 3 degrees of freedom is 7.815. But we don't really need that to calculate the p-value. What we need is the 3 degrees of freedom. Now, by the way, if you use the traditional approach and you go ahead and calculate the test statistic yourself, it's going to be 6.402. The critical value is 7.815. So once again, we failed to reject the null, which means that the data really are normal with a mean of 5% and a standard deviation of 10%. But why don't we go ahead and calculate the p-value based on the data that we just came up with. So I'll sneak that in down here. So set L1 equals to observed data. L2 is expected data, or expected frequencies, I guess I should say. And then go to, as we saw before, stat tests chi-square goodness of fit. And remember, what it's going to ask you for is 3 things. Observed, L1, expected, L2, DF, which remember in this case is 3, and calculate, of course. And when you do that, you'll get, once again, it'll remind you that the chi-square test statistic, which we don't really need, just in case you were wondering, is 6.402, let's say, 403. But the key here is that the p-value is 0.0, or actually it just says p. P equals 0.0936. And of course, that tells us that it's too high for us to reject the null. That the data are normal with a mean of 5% and a standard deviation of 10%. All right, so I think that might be the way that people want to go, rather than doing the test statistic by hand. But you can do it either way, of course. You always have that option. But I don't know about you, but I think it's so much more straightforward this way. But, this one, it's not really doing everything for you, because you do have to calculate those normal probabilities. So you really are still doing most of the work, just not all of it. So again, you can use the traditional approach. You can see that how the test statistic was actually calculated, but we don't really need it because we can use the p-value approach. So that was really all we needed to say about goodness of fit tests, because you can see they're all done exactly the same way. The only thing that is different from one case to the next is the expected frequencies are taken from whatever distribution you're working with. So once you've got these done, you can just throw all these values into your lists. And of course, you have to calculate the degrees of freedom as well. And then the GOF function will do the rest for you. So while this topic looked very scary when we first started it, it really isn't. It's like so many other topics we've done. It looks terrifying at first, and then you do it a few times and you say, come on, this is too easy. It can't be for real. All right, well, that was good. So I'll tell you what, let's go to the next section, which is 13C, where we're going to discuss a very different kind of hypothesis, something, again, we've not seen before. So you're probably wondering, what else could there possibly be for us to do with these tests? Just save this real fast. So this way, I'm giving it a separate title so that I can post separately the slides with the notes that we've just created today. And of course, you saw that I did add more content there. So I want to make sure they don't get lost. All right, anyway. So here we're going to do something completely different. We're going to test whether or not two populations are independent. Now, if you remember from chapter 11, remember we went through and we did a bunch of testing. And in most of the cases, we were assuming that two populations were independent of each other. Sometimes that assumption may not be perfectly valid. It's one of those things where you can't just say, well, it sounds like they're probably independent. Ideally, you should have a formal test to prove or disprove whether or not your populations are independent before you carry on with any type of testing. So here we're going to find out exactly how that would be done. Now, this section, unlike the section we just finished, where the calculator is helping you up to a degree, but you're still doing a lot of the work yourself. Here, we're going to find out pretty quickly that the calculator can essentially do everything for you. But first, we have to understand what exactly is going on behind the scenes. So in other words, before I show you that special technique with the calculator, we need to understand what exactly is happening when we calculate the test statistic. Otherwise, it won't make any sense to you. All right, so we're trying to find out if two populations are independent. So we'll start out with the null hypothesis that the variables are independent, and the alternative is that they're not. So in this sense, it's set up like a goodness of fit test. The null is that they are independent, and we'll assume that unless we find evidence that they're not, strong evidence that they're not. Which, by the way, is reverse of what we normally see. Normally, the hard proof is required to, show something that we're interested in proving. Here, we're essentially assuming that our assumption is correct of independence, and we're searching for evidence that it's not correct. So this is basically reverse of what we normally see. Okay, so it's either yes or no, which means that this is also a right-tailed test only. But the interesting part is the test statistic. Okay, we're going to set up a table. Now this time, the table is going to be more complicated because we're looking at two different characteristics at the same time. So here's an example that I dreamed up. Suppose that men and women, Starbucks wants to know if men and women tend to prefer the same styles of coffee. So we pick a sample of 100 men and 150 women, and we set up what's called a contingency table to see how much or which flavors they prefer. All right. And of course, the point of it is to see how similar they are to each other. Now, here's the table. These are the observed frequencies. And you notice how here all of a sudden we have two rows. And in principle, we can have as many rows as we want. And the same thing with the columns. There's only three, but we can have as many as we want. So what we're trying to find out is based on these three flavors, Komodo dragon, French roast, and Sumatra, out of the 100 men, you can see that 30 of them preferred Komodo dragon, 40 prefer the French roast, and 30 prefer the Sumatra. Among the women, there's 150 of them, 40 like Komodo dragon, 80 like the French roast, and 30 like the Sumatra. So the question is, are the proportions equal to each other? In other words, is this proportion of men who like the Komodo dragon the best the same as the women? And the same thing for the French roast, same thing for the Sumatra. Well, it's hard to tell just by looking at these numbers. They're not obviously the same, but are they far enough apart to conclude that their preferences are different? Now, if we are unable to reject the null, by the way, it simply means that there's no relationship between flavor preferences and genders. Okay, it's the same for both. If we reject the null, it means that there's a tendency for women to prefer different flavors than men. Okay, so, and obviously Starbucks needs to know that because it helps them decide how to market their products. All right, so now the test statistic looks interestingly similar to what we had before, except now because there's more than one row, we need two indexes now. We need a row for an index for the column, which is here. And this is for the rows. So the subscript, this is row I, and this is column J. Same thing with the E's, of course. So because we have at least two rows and multiple columns, we need to have two subscripts or two indexes, one for the row, one for the column. And that means we have to add through the rows and through the columns, but the basic logic is the same. So already it's looking frightening. Remember, this is the one where the calculator can actually bypass a lot of the work for us. So do not be alarmed when you see what you have to go through to calculate these expected frequencies. It's a bit of a mess. I'll tell you right up front, it's a bit of a mess. So, but like I said, the calculator will take care of that when it calculates the p-value. In fact, when you see this one, you're going to say, you know what? This calculator is the best thing that I own. It is so important. It is so powerful. It is so useful, and it's so inexpensive. It's the best thing I've ever bought in my life on a dollar per dollar basis. All right, now we're going to need some terminology here. we're going to let represent n represent the number of observations in a given row. Okay, ni is the number of observations in that row. Eij, of course, is the expected frequency if we're in row I in column J, and then Pj is the proportion of the total number of observations that belong in a given column. So, for example, let me just show you with this table. N, all right, let's do it this way. P1 would be 70 over 250. P2 is 120 over 250. And then P3 is 60 over 250, 0.24. So this basically means that for the entire sample, 28% prefer the Komodo dragon, 48% prefer the French roast, and 24% prefer the Sumatra. Now, the logic of this test is that being the case, we would expect 28% of the men like Komodo dragon best, and 28% of the women do as well. All right, so that's what we're trying to find out. Now, as far as the ends are concerned, this is N1, this is N2. N simply means the row total. So therefore, let's say the expected number of men who prefer Komodo dragon. By the way, let me just fill these in too. These are the observed values. This would be 011, 012, 013. Why? Because the 1 represents the row. All right, remember, it's row column. 11, 12, 13. This would be 21, 22, and 23. Now, that being the case, E11, the proportion, the number of men we would expect to see in this category, right here, would be N1. Let me repeat this up here real fast. E in any column in any row equals Ni Pj. So this one will be 100 times 0.28. That means if the two are independent, you'd expect 28 men to prefer the Komodo dragon. E12 is 100 times 0.48. That means we should expect to see 48 men preferring the French roast. Now, I'm running out of space here. I just want you to see what these calculations are all about. We'll do the rest of these on a slide coming up very quickly. But this way you can at least see how the process works. The E's are the result of the row totals and the proportions in each column. And we'll run through and fill them all out. And then we have the test statistic, the dreaded test statistic. Oh my God. So you can see it is turning into quite a mess. So, all right, I'll tell you what, let's do one more of these E's for the men, and then we would need to do them for the women as well. E13 is N1P3. which is 100 times 0.24, which is 24. Then we would go through the women. Okay. So you'd have E21, E22, and E23 doing the same thing. So let me scroll ahead here and show them to you, those calculations. For example, E21, N2 times P1. Remember, there's 150 women in that row. 28% prefer Komodo dragon in the entire sample. So that means we'd expect to find 42 women drinking the Komodo dragon, 72 women drinking the French roast, 48% of 150, and 36 drinking the Sumatra, 24% of 150. So I put them all together in a nice little table for you. And you can see they do look pretty close to each other. So now we have to fill them into those terrifying, the terrifying test statistic. Well, what happens if we do that? There it is. So here's what you have to do. Look at it. Look how many of them there are. What do they represent? Oh, don't you worry. In a minute, I'm going to show you how the calculator handles this. Oops. Yeah, no, that's right. That's right. Okay. So then when you add them up, you get your test statistic, which is about 4.96. Again, not very large for the chi-square distribution. And then you're going to have a critical value. The critical value is pretty straightforward. Again, is always what you're really after is the degrees of freedom. That's the challenging part. So you've got chi-squared alpha. The degrees of freedom is r minus 1 times k minus 1. R is the number of rows in our table. And this is the number of columns. Remember, when we started out, you look at the observed frequencies, and this is for the observed frequencies. There were 2 rows and 3 columns. That's all you need to know. And not the totals, but there's 2 rows for the men, 1 row for men, 1 for women, 2 rows total, 3 flavors of coffee, 2 rows, 3 columns. All right, so in our example, that ends up being 2 minus 1 times 3 minus 1, which is just 2. And with alpha is 0.05, we've already seen this one earlier. We can look it up again if we need to. That was the 5.991. And guess what? Once again, we're unable to reject the null hypothesis. And that means that the data are independent. In other words, the genders and the preferences for the flavors are independent of each other. In other words, the proportion of men who prefer each of those 3 flavors is the same as the proportion of women. So as far as Starbucks is concerned, there's no point in advertising separately to men and women because they like the same flavors. Now it's time for the good old calculator. How will the calculator help us with this? Well, you'll be shocked and amazed to see this, how easy it is. So, but we're going to use a button you've never seen before. Be prepared to be amazed. All right, you're going to hit second. And then if you look over the far left, underneath the math button, you'll see that there's a button labeled X-1, which means the inverse of X. Directly above it, it says the word matrix, which you should have encountered in high school somewhere along the way. A matrix is basically a square object that usually contains information about simultaneous equations, but it can be used for a lot of purposes. Hold on one second. It's giving me trouble. I want to make a superscript here, and of course it's giving me grief. There you go. Sometimes you just have to show who's boss. You know what I mean? All right. So when you get there, you're going to see, go to the edit menu. Now, if you notice in the edit menu, matrix A is listed as 2 rows and 3 columns. That's what we need. So we don't change anything. Hit enter. And now you're going to literally type, you see that object that you're seeing there, you're going to type the observed frequencies. Okay, so let me scroll it back so you can see it again. Just type in those numbers, 30, same order, 40, 30, 40, 80, and 30 again. Okay, now when you're done, you can escape from this mode by hitting the second mode button. Okay. Now, I know we're running out of time, so once you're finished that, you hit the second mode to get out of that mode. And then we're going to go to second vars, and you'll scroll down to, oops, sorry, no, not second var, sorry, stat tests. The one you're looking for is C, chi-square test. Okay, so choose that. And, oh no, I hit the wrong one. Sorry, hold on. Okay, now if it says observed A, this is what you want. Then just hit the calculate button. Otherwise, change it. And when you hit the calculate button, it comes back with the chi-square result. Which is 4.96. And then the most important number, the p-value 0.0837. It also, of course, reminds you that the degrees of freedom is 2. Actually, let me do this. And the most important thing is that since the p-value is greater than alpha, do not reject the null hypothesis. Of independence. So in other words, the flavor choices are independent of gender. So if you notice, this time, all you had to do is type the observed values into matrix A, and it took care of the rest for you. Wow. So in other words, that is the easiest of them all, because this one requires the least amount of work. I mean, you have to understand what you're doing, but what it actually did, which you didn't notice, in fact, if you want to go back to the matrix button and look in B, you'll see that it contains the values that we determined earlier down here in the bottom. Go look at it. Go to matrix, hit B, enter, and you'll see it contains a matrix 28, 48, 24, 42, 72, 36. In other words, it did all this for us. And it then turned around and used that to come up with the test statistic and in turn the p-value. So it really did everything. Wow. Now I said before, you're suddenly going to realize that this is the most amazing thing you've ever bought in your life. And I think you see why I said that. Because wow, just think of all the work it saved you. Yeah, that's right. So anyway, that's it for the goodness of fit. Well, you know what? I just realized that that was it for 13. There's just those 3 sections. So that means that, frighteningly enough, we are actually going to be ready for the second midterm even sooner than we thought. So when we get back on Friday, we'll have to do some planning, because of course we still have to do a large number of problem sets and sample final, midterm rather. And we still may want to still go back and revisit this stuff again on Friday rather, to go over it one more time, because we did go through it kind of quickly. But yeah, it won't be that much longer before midterm number 2 is ready. So definitely we won't have to worry about Easter, that's for sure. So all right, I guess I'll just see you then on Friday then. All right. So unless you got last minute questions, I'll see you all hopefully in person on Friday.
Have a good one.
All
Have a
right.
good one, Professor. Thank you.
Thank
Okay,
you.
bye.
Bye. Thank you.
Later. Oh, I see 2 chats that I didn't see. Oh, that's okay if you're late. Yes, I did. It actually keeps track of everyone who's here. I don't even have to worry about it. Well, all right, that was good.